You know, think about water for a second. It's everywhere. It covers over 70% of our planet. It's about 60% of our bodies. We use it so much we barely even notice it anymore. And yet, this one simple molecule is the absolute foundation for all life as we know it. So, why? That's the big question we're going to dig into. How does something that seems so basic, just H2O, get all these complex, life giving properties? How does it support everything from a tiny microbe to a giant redwood? Okay, let's dive in. To really get a handle on water's power, we've got to start small. I mean, atomically small. We're going to unpack the H2O and see what's really going on under the hood. So, on the surface, it seems pretty straightforward. You've got one big oxygen atom, and it's bonded to two smaller hydrogen atoms. They're sharing electrons in what we call polar covalent bonds. But here's the first major clue, the thing you have to remember. The molecule isn't a straight line. It has this very specific bent shape. And as you're about to see, that simple little bend, well, it changes absolutely everything. Now we're getting to the single most important property of water. Seriously, if you remember one thing, make it this. We're talking about polarity. What this means is that every single molecule of water acts like a tiny, tiny magnet. To understand why it's a magnet, we need this one word, electronegativity. You can just think of it as an atom's greediness for electrons. And in the case of water, the oxygen atom is way more electronegative than hydrogen. It's a total electron hog. So even though they're supposed to be sharing electrons, oxygen is pulling them way, way closer to itself. So what's the outcome of this constant tug of war? Well, since those negatively charged electrons are spending all their time buzzing around the oxygen atom, that end of the molecule gets a slight negative charge. And the poor hydrogen atoms, with their electrons pulled away from them, they get left with a slight positive charge. And boom, just like that, you have a molecule with two poles, a positive end and a negative end. It's polar. And this brings us right back to that bent shape we talked about. That very specific angle, 104.48 degrees, is so crucial. See, if water was a straight line, the two positive ends would be on opposite sides and their charges would just cancel each other out. The molecule would be nonpolar. But because of this precise bend, the positive and negative charges are kept separate, creating this permanent polarity. That's the secret to water's magnetism. So we figured out that a single water molecule is a tiny magnet. But, you never really find just one water molecule floating around by itself. So what happens when you get billions of them all together in one place? Well, this is where the real magic starts. It's exactly what you'd expect with magnets. The slightly positive hydrogen end of one water molecule is drawn to the slightly negative oxygen end of another one nearby. This attraction is called a hydrogen bond. Now, it's not super strong, but I want you to think of it like molecular Velcro. A single piece is weak, but when you get billions of them holding on together, they become incredibly powerful. This quote really just nails the core idea, right? It's a simple cause and effect. The polarity we just figured out leads directly to this attraction. And this attraction, this hydrogen bond, is responsible for so many of water's crazy, unique properties. And this isn't just some theory. You can actually measure the results. Take a look at this data on surface tension. You know that weird skin on the surface of water that lets insects just walk right on top of it? That's surface tension, and it's caused entirely by those hydrogen bonds pulling all the surface molecules inward. And check it out. As you heat the water up, the molecules move faster, those Velcro bonds break more easily, and the surface tension drops. It's a direct physical proof of that molecular stickiness. Okay, so water is sticky. Let's see how that stickiness leads to one of its most famous superpowers, its ability to dissolve just about anything. There's a reason they call it the universal solvent. Because water is polar, it loves to interact with other polar things, substances like salt and sugar. We call these things hydrophilic, which literally means water-loving. The tiny water magnets just swarm these molecules, pulling them apart and dissolving them. But water is not a fan of nonpolar molecules, things like oils and fats. We call those hydrophobic, or water-fearing, because they don't have any charges for the water molecules to grab onto. And we've all seen this 1,000 times, right? You mix oil and water, and they just refuse to mix. What's actually happening is that the water molecules are so much more attracted to each other that they basically push the oil molecules out of the way, forcing them to clump together. And get this, that simple act of separating is fundamental to how the membranes of every single cell in your body work. It's wild.
So far, we've kind of treated water molecules like these neat, stable little things. But the reality is a little more dynamic. Water actually has a kind of secret double identity, and it's absolutely crucial for the chemistry of life.
So, in this huge sea of water molecules, every once in a while, something strange happens. One water molecule will literally pass off a proton, that's one of its hydrogen nuclei, to its neighbor. The molecule that loses the proton becomes a negative ion, and the one that gains it becomes a positive ion. Now, this doesn't happen very often to any one molecule, but it's happening constantly across the whole system.
It took science a while to puzzle this one out. The first idea came from Arrhenius way back in 1884. He had the basic concept right, but it took about 40 more years for Bronsted and Lowry to refine the idea, realizing it was a transfer between two water molecules, not just one falling apart on its own. It's a perfect example of how scientific models get better and more accurate over time.
So why should you care about this rare little reaction? Well, because this tiny but constant balance of these two ions in pure water, that's our baseline for what's neutral. It is the literal foundation of the entire pH scale, the thing we use to measure acidity in everything from our own blood to the soil in our backyards.
Okay, we have covered a lot of ground here, from atoms all the way up to chemistry. So let's pull it all back together and finally answer that big question we started with. Why is water the key to life? This right here, this is the whole story. It's this incredible chain reaction. It all starts with that simple 104.48-degree bend in the molecule. That bend creates polarity. Polarity allows for those hydrogen bonds, that molecular Velcro. And those bonds make water super sticky and an amazing universal solvent. That means it can dissolve and transport all the chemicals that life needs to function. It literally creates the perfect liquid stage for the entire complex play of life to unfold. It's really an incredible thought, isn't it? All of water's amazing, life-giving complexity comes from one tiny, simple fact about its shape. It makes you wonder, what other huge secrets are hiding right there in front of us in the everyday things we completely take for granted? Thanks for joining us for this explainer.